In this video, we will go over some practice problems for the final exam. The first question over here is about CPU scheduling. So we are given a new CPU scheduling algorithm called longest job first, which schedules the jobs with longest CPU burst first. So this is opposite of the shortest job first. So for instance, if we are given three processes P1, P2 and P3, and let's say the CPU burst of P1 is 10, of that of P2 is 30, and P3 has a CPU burst of, let's say, 15. So this LJF algorithm, longest job first, will schedule it in this order. So P2 has the longest CPU burst, so this will go first. Next P3, which has the next longest burst, and finally P1, which has the shortest burst, will go at last. This is how this scheduling algorithm works. The question is asking us, would this algorithm favor IO bound processes or CPU bound processes? Recall that typically the IO bound processes have short CPU bursts, and that's because they spend most of their time during their execution lifetime waiting for IO. As opposed to this, the CPU bound processes, they have long CPU bursts, and because this scheduling algorithm is ordering jobs in descending order of their CPU bursts, it is bound to favor the CPU bound processes. In other words, this algorithm is giving preference to processes that have longer CPU bursts, and that is why this will favor CPU bound processes. The answer to this question is summarized over here. The second question is a continuation of the first question. Here we are given a preemptive variant of the longest job first algorithm that we talked about previously. Among all the processes in the ready queue, the one which is longest is scheduled to run on the CPU. However, in addition to this, during execution of this process, if another process which has a longer CPU burst than the remaining CPU burst of the executing process arrives, then the currently executing process is preempted. This is how the LRTF algorithm, longest remaining time first algorithm, works. The question is asking us, could this algorithm cause starvation for either IO bound processes or CPU bound processes? The short answer is this kind of scheduling algorithm can starve all kinds of processes, IO bound and CPU bound processes alike. Let's take an example to understand. Let's say we have three processes P1, P2 and P3 in our ready queue, and let's say their CPU bursts are, let's say, 10, 20 and 30 milliseconds. So the longest job first algorithm will pick process P3 for execution. Let's say P3 starts executing, and assume that this is a very busy system. So every millisecond a new process is added to the end of this ready queue. So let's say the ready queue is going this way. So P4, P5, they keep coming in. Almost every millisecond a new process comes in. Now as this process P3, the currently executing process, as this approaches completion, let's say this P3 has run for 28 milliseconds or 29 milliseconds, and only one more millisecond remains to go. It is very likely that any new process, there are processes coming in every millisecond, it is very likely as this executing process approaches completion, any new process that joins the ready queue would have a CPU burst longer than the remaining time of the currently executing process. So for example, let's say P6 comes in and P6 requires 6 milliseconds, which is greater than the 1 millisecond remaining for currently executing P3. This will cause preemption of P3. P3 will be moved back to the ready queue, and the next long process, let's say P2, will be scheduled. So close to completion, all kinds of processes are very likely to be preempted in a busy system where new processes keep coming in, and because the executing process was close to completion, its remaining time would very likely be less than the new execution time or the CPU burst of the newly arriving process. Therefore, all kinds of processes would starve for completion in this kind of scheduling algorithm. The answer is also summarized over here. The third question here is about caches. We are given a fully associative cache that has 8 cache lines. It uses LRU replacement policy. The memory addresses are 32 bits long. It's a byte addressable memory, and the block size is 128 bytes. The question is asking us how many bits are needed for the block offset. Recall, in a fully associative cache, the memory addresses are divided into two parts, the block offset and the tag. The block offset has log to base 2 of block size number of bits, and all the remaining bits are for the tag. In this case, the memory is byte addressable and each block has 128 bytes. So the block size is 128. Therefore, the block offset would be log to base 2 of 128, which is basically 7 bits. Recall that 128 is 2 to the power 7. That's why log to base 2 of 128 is 7. Note that we just need to know the size of the block and whether this is a byte addressable memory or what is an addressable memory to solve this problem. There is a lot of extra information which is not needed here, which is provided in the question. So for example, we don't need to know the number of cache lines, also the replacement policy and so forth. Here is a question about average memory access times in presence of caches. So we have a cache. If the data is found in the cache, it takes 10 nanoseconds to retrieve it. If we have to access the main memory, then it takes an additional 300 nanoseconds. The cache has a hit rate of 80%. The question is asking us what is the average memory latency for this system, assuming all memory references first go to the cache. As we have seen in the class, the average memory latency is going to be a weighted average of all the access times for accessing the data from the cache and accessing the data from the main memory. Let's assume that the data is found in the cache. If it is found in the cache, it will take 10 nanoseconds. As opposed to this, if the data is not found in the cache, we have to go to the main memory. Then it will take, we first access the cache and we find that it was a miss, which took 10 nanoseconds. And then it will take 300 nanoseconds additional time to get the data from the main memory. So this is the time that it takes to get the data from the main memory. The probability of finding the data in the cache is 80% because the cache hit rate is 80%. So this is, let's multiply this by 0.8, and the probability of not finding the data in the cache and therefore going to the main memory is 20%, 100 minus 80. So that's this. So the weight of the second term here is going to be 0.2. Now this is the weighted average. So 0.8 into 10, this is 8 plus 0.2 into 310. This is basically 8 plus, so 0.2 into 310 is 62. So this is going to be 70 nanoseconds. This is the average memory latency. The answer is also given over here. Here is a question about CPU scheduling. We are given 5 processes P1 all the way to P5. Their CPU bursts are provided and their relative priorities are also given here in this table. The question is asking us to draw a Gantt chart showing the execution of these processes for FCFS, shortest of first, non-preemptive priority scheduling, and round robin with a time quantum of 1 millisecond. After doing that, we are asked to compute the average wait time and the average turnaround time for all of these processes for these algorithms. For solving these questions, we will assume the processes, they all arrive at time 0, since the arrival time is not given. Also, we will assume that they are admitted in the system in the order specified. So P1 followed by P2 followed by P3, then P4, and finally P5 was admitted in the system. Let's start with FCFS algorithm. The FCFS algorithm would schedule these processes in their arrival order. Let's say this is time 0. First P1 arrives, so P1 would be scheduled and it will finish somewhere here at time 8. After this, P2 would be scheduled. It will run for 6 time units, so 8 plus 6, it will run until, let's say, 14 over here. Then P3, it would run for just 1 time unit, so this was P2, this is P3, which will finish at 15. Then P4 will be scheduled. After that, it will start here and it will go all the way to 24, and finally P5 will run for 3 time units and it will end here somewhere, let's say 27. So this is the Gantt chart. Now the average wait time, process P1 did not have to wait, it started immediately at time 0. So the wait time for P1 was 0. P2 started at time 8, so it had to wait for 8 time units. P3 had to wait for 14 time units. P4 had to wait for 15 because it started at 15, and P5 started at 24, so it had to wait for 24 time units. So let's compute an average of all of this, divide this by 5, and whatever we get, that's the average wait time. So this would be 12.2 time units. Let's think about the average turnaround time. So P1 finished at time 8, so its turnaround time was 8. P2 finishes at 14, so its turnaround time is 14. P3 finishes at 15, so its turnaround time was 15. P4's turnaround time was 24, and P5's turnaround time is 27. So add all of these and divide by 5. Whatever number we get, that's the average turnaround time for FCFS algorithm for these processes. So this would be 17.6 time units. The answer is also summarized over here. Next we have the shortest job first algorithm. As you would know, this would schedule the processes in the ascending or increasing order of CPU bursts. So the shortest job would be scheduled first. So in this case, P3 has the smallest CPU burst, so P3 would be scheduled first. Next P5 would go. After that, the next smaller burst is P2, so P2 would go third. P1 would go fourth, and P4, which has the longest CPU burst, would go last. This would go fifth. So let's use this information to draw the Gantt chart. Let's say this is time 0. First we schedule P3, so P3 starts here. It has just one, its CPU burst is just 1, so it will finish at time unit 1. After this, P5 would go. P5 has a CPU burst of 3, so it will finish at 1 plus 3 4. Next we have P2 coming in. It has a CPU burst of 6, so it will start at 4 and it will finish at 4 plus 6 10. After that we have P1 coming in, which has a CPU burst of 8, so this will start at 10 and finish at time 18. And finally we have P5 with, I'm sorry, not P5, we have P4, which has a CPU burst of 9, so this will finish at, it will start at 18 and it will finish at 27. The average wait time would be given by, so P3 did not have to wait at all, so its wait time is 0. P5 had to wait for 1 time unit, it started at 1. P2 had to wait for 4, it started at 4, so its wait time was 4. P1 started at 10, so its wait time is 10. P4 started at 18, so its wait time is 18. So the average of all of this would be, this is 33 divided by 5, which is basically 6.6. Similarly, the average turnaround time is given by, so P3 finishes at 1, so its turnaround time was 1. P5 finishes at 4, its turnaround time is 4. P2 finishes at 10, so its turnaround time is 10. And P1 finishes at 18. Similarly, P4 finishes at 27, so its turnaround time is 27. So divide all of this by 5. Is 60 divided by 5, which is simply 12. A quick note about the turnaround time. Recall that the turnaround time is given by finish time, or basically the termination time minus the arrival time. In this case, however, we are assuming that all the processes arrive at time 0, and that is why we are simply looking at the finish time in order to compute the turnaround time. However, in the exam, you should look at the proper arrival time. If the processes are not arriving at time 0, their turnaround time would be computed using this expression. The answer for this question is also summarized over here. Next, we have non-preemptive priority scheduling. In this case, we will assume that a smaller priority number indicates a higher priority. So for example, here P2 has the highest priority, so P2 would go first, it would be scheduled first. Next, both P3 and P4 have the same priority. Therefore, in this case, we'll break the tie using FCFS. Since P3 was admitted to system first, it would go before P3, before P4. So next P3 will go, and third P4 will be scheduled. After this, P5 has the next higher priority, so P5 goes fourth, and then finally P1 is scheduled at the end. Let's use this information to draw the Gantt chart. This is time 0. P2 goes first. It has a CPU burst of 6, so it will start at 0 and finishes at time 6. After that, P3 is scheduled. It has a CPU burst of 1, so it starts at 6 and finishes at 7. Next P4 is scheduled. It has a CPU burst of 9. It starts as 7 and finishes at 16. So here, then we have P5 coming in, which has a CPU burst of 3. It starts at 16 and finishes at 19. And finally we have P1 coming in, which has a CPU burst of 8. So it starts at 19 and finishes at 27. The average wait time and turnaround time would be computed similarly. So here again P2 had a wait time of 0, P3 started at 6, so its wait time is 6, P4 started at 7, P5 had to wait for 16 time units, and P1 had to wait for 19 time units. So just divide all of this, add this and divide by 5. This gives a 48 divided by 5, which is 9.6 time units. Similarly, average turnaround time is given by P2 finishes at 6, so its turnaround time is 6. P3 has a turnaround time of 7. P4 finishes at 16, so turnaround time of 16. P5 finishes at 19, and P1 has a turnaround time of 27. Add all of this and divide by 7. Sorry, divide by 75 by 5, which is simply 15. Once again, a similar note on the wait time. Recall that the wait time is given by, wait time is basically turnaround time minus the burst time. However, in this case we can compute the turnaround time, the wait time, simply by looking at the finish times, because we are again assuming that the arrival time of all the processes is 0. That's why even if you do this turnaround time minus burst time, you'll simply get the starting time of the process execution, and that's why this is the simpler way that we can use here. However, in the exam, again, you should be careful. If the arrival time of all the processes is not 0, then you should use this expression to compute the wait times. The answer is also summarized here. Finally, we have the round robin algorithm with a time quantum of 1 millisecond. Recall, in round robin algorithm, each process will get a one time quantum, which is basically 1 millisecond in this case. So each process will get to run for 1 millisecond. It will be preempted, and the next process will be scheduled. And because the processes arrived in this order, P1 to P5, they would be scheduled within each window in this order. So for instance, in this case, the Gantt chart would look something like this. At time 0, first P1 would be scheduled. It would be allowed to run for 1 millisecond. Then it would be preempted. Next P2 would be scheduled for 1 millisecond. It will be preempted at time 2 milliseconds. Then P3 will go. It will be preempted at time 3. Then P4 would be scheduled, would be preempted at time 4. Then P5 would be scheduled and would be preempted at time 5. So this is the first window of all the 5 processes. Note that P3 just requires 1 millisecond. So at the end of this first round, P3 will finish. So in the second round, we'll just have P1, which would be starting at 5, ending at 6. Then P2 would start at 6 and preempted at 7. P3 is not, it has finished, so P4 would go next. It started at 7, end at 8, or preempted at 8, and then P5 would start at 8 and preempted at 9. So this is the second window, and this continues until all the processes finish. So the complete Gantt chart is shown over here. So the first window finishes over here. After this, so at the P1 finishes in this window. The next window finishes in at here. This is the second window. The third window finishes here. After this window, P5 will finish. Now you see only 3 processes are scheduled: P1, P2, P4, P1, P2, P4. So this is the fourth window, the fifth window. This is the sixth window. After the sixth window, P2 would finish. So only P1 and P4 would be remaining. So P1, P4, P1, P4. So this is one window. This is the second. This is the next window. And now at this second last window, at the end of this eighth window, P1 will also finish. So note that now after this, P4 has just one more time slot remaining. So it will run and finish at 27. So this is the last window, and P4 finishes here. For the round robin algorithm, the wait time computation would be a little more involved than the previous examples that we have seen. So let's focus on P1 and let's see how to compute the wait time for process P1. So P1 started here at time 0. initially in the first round it did not have to wait at all. So for P1 initially the wait time was 0, but then it was preempted at time 1, and then it had to wait for 1 2 3 4 time or 4 milliseconds before it was scheduled again and at time slot 5. So again, so its wait time was 4 for the before the next round. It was again started at 5 but preempted at 6. Before its turn at time slot 9, it had to wait for 1 2 3 more milliseconds. So add this to its wait time. Then again it was preempted at 10, and it had to wait for 1 2 3 more milliseconds before it was again scheduled at time slot 13. It was again preempted at 14, and then it had to wait for 1 2 more milliseconds before it was again rescheduled at 16. Ran for 1 millisecond, again preempted at 17, had to wait for 2 more milliseconds, so add 2 more milliseconds. Again ran at time in slot 19, preempted at 20 millisecond, then again we had a wait of 2 more milliseconds, so add this to its wait time before it was scheduled at time in slot 22. Then again it had to wait for 1 millisecond here before it was rescheduled in 24, and then it finished at time 24 milliseconds. So its total wait time, let's just add these terms. It will come to this 4 plus 3 plus 3 is 10, and this is 6, so 10 plus 16 plus 1 17. So 17 milliseconds is the total wait time for P1. Similarly, you can compute the wait times for P2, P3, P4 and all the other processes. The computations are summarized over here. The average wait time is straightforward. Once you have the wait times for these individual processes P1, P2, P3, P4, P5, just add these all and divide by 5. So the answer is 12.4 milliseconds. That's the average wait time for all these 5 processes in round robin scheduling. The average turnaround time is straightforward. Turnaround time is simply finish time minus the arrival time. Because the arrival time is 0 for all the processes, we can just look at the finish time. So P1 finished at after 25 milliseconds. So the turnaround time for P1 was 25. P2 finished after 21 milliseconds. So turnaround time is 21 milliseconds. P3 finished after 3 milliseconds. So its turnaround time is 3. P4 finished here at 27. So its turnaround time was 27. And finally P5 finished at 13 milliseconds. So its turnaround time was 13. So let's add all of this, comes to 89. Just divide this by 5 and the wait time would be, average wait time would be 17.8 milliseconds. The first question over here is, as process design technology allows engineers to put more transistors on a chip, microprocessor companies are increasing the number of cores on each chip. What other feasible choices could they have made instead? So basically what this question is saying is, with every passing year, as our process design technology evolves, the size of the transistors is shrinking. So essentially, in the same given chip area, let's say this is our chip area, we are able to fit more and more transistors with every passing year. Increased number of transistors basically translates to increased functionality that can be implemented on the same chip area. So the question is, how can we, what are several different ways in which this flexibility can be used? So the way it is currently being used, as the question says, is, let's say last year, so I'm just this is just a hypothetical example. Let's say last year the transistor technology was at a place where in this given chip area we could implement 2 cores, only 2 cores. We could only fit in so many transistors that were sufficient for 2 cores. But let's say this year, with the evolution of this process design technology, now we are able to fit 2 times more number of transistors in the same chip area. So one possible way of using this evolution is that in the same chip area, instead of 2, we now implement 4 CPUs or 4 cores. Now this is obviously one way of increasing the functionality. What else could we have done? So well, the other obvious thing we could have done is, let's say we kept the number of cores constant. So let's say we still implemented 2 cores, but then we could have increased the size of the cache on chip, right? So maybe we could have increased the size of L1 L2 caches, and maybe also the size of, let's say this is the shared L3 cache, right? So this is another way of increasing or improving the functionality on the chip. So the question is, why this is not done, right? Why did the designers choose to go with increasing the number of cores and not increasing the size of the cache? So the main reason it is not as beneficial to increase the size of the caches is doubling the size of cache will certainly help improve the hit rate, and obviously, as you would know, increased hit rate means that we can satisfy more of our data and instruction requests from the faster caches, and we have to go to the slower main memory less frequently. However, the problem is, if you think about this, let's say right now your L1 cache is let's say 64 kilobyte in size, and let's assume that you double it, you make it 128 kilobyte. This L1 cache, which is 64 kilobyte, typically this would already have a hit rate of more than 90%. Okay, and if you double it, this hit rate will go up from 90% to, let's say, 93%, right? So just by doubling the size of the cache, the hit rate does not double. There is not so much room. You will go from 90 to 92, 93 or 95%, right? So the gains that you're getting are marginal. As opposed to this, if you deploy these additional cores on the same chip, then on each additional core you are able to execute additional processes, additional threads simultaneously in parallel, right? So you have increased amount of parallelism, and you can run more number of processes and threads, which will provide much greater computation improvement as opposed to just enhancing the size of the cache. So that's the main reason that designers have chosen to go with implementing more cores as opposed to increasing the size of the caches, for example. The answer is also summarized over here. So the next question over here is, why do interrupt service routines have priorities associated with them, whereas normal procedures do not have priorities? So let's think about how processes execute functions, right? So let's say in your code you have a function fun, and let's say this function calls fun1, and then it calls fun2, let's say, right? So the way this works is, when your code reaches this point of fun1 call, it will jump to function fun1, execute it completely. Whenever fun1 completes, it will return, and then it will start executing this next function called fun2. Whenever fun2 finishes, it will return and start executing the next line of code in this function, in this function fun, right? So the thing is, with normal procedures, the order in which function should be called is completely dictated and determined by the program itself. As opposed to this, with interrupts, let's say the CPU is let's say CPU right now is serving some interrupt I, right? And the CPU is not yet done, and in the meantime, in between, let's say another interrupt J arrives. Now the question is, CPU doesn't know whether it should keep executing, keep serving interrupt I, or should interrupt I be suspended and interrupt J be served instead. So some way is needed for the CPU to decide which of these two interrupts is more important in some sense or more urgent, and this way is basically the assignment of priority to the interrupts. So that is why priority priority assignment is important in interrupts, and it is not important in normal procedure calls. Why do IO devices place the interrupt vector on the bus? So the main reason this interrupt vector is needed is for identification of the device that is interrupting the CPU. So recall, in our systems we have, let's say, one CPU, and there is an interrupt line. Let's say this is the interrupt line of the CPU. Several IO devices are attached to this one interrupt line. Let's say you have a hard disk here, you may have some optical drive here, or you may have some other IO devices, keyboards and so forth, right? There are so many IO devices and number of IO devices that are connected to the same interrupt line of the CPU. So all of these, any of these IO device, whenever it needs to send an interrupt to the CPU, it will have to assert a signal on this interrupt line. Now the problem is, the CPU receives the interrupt, but then how does the CPU know which of these devices has caused the interrupt, whether it is the hard disk, or is it a keyboard, or is it some other IO device? So the way these IO devices identify themselves is with the help of this interrupt vector. So as we discussed in the class, once the interrupt has been acknowledged, the interrupting IO device will place a small integer on the bus, which will help the CPU recognize or identify the device. This question is about cache replacement policies. We are given a string of memory references, and we have to compare the number of cache misses that these memory references would see with the LRU first in first out and the optimal page replacement algorithms. We are assuming a fully associative cache which has 4 cache lines. Let's start with the LRU page replacement or the cache replacement policy. So let's assume we have this 4-line cache. This is let's say lines 1, 2, 3, and 4. The first address, initially the cache is empty, so the first address reference, which is 1, this is going to be a miss, and let's bring it into the first line that is available. And let's also keep track of the accesses. So when we mark a 1 in front of a cache line, it was just now accessed. The cache lines that were not accessed, those are marked with a 0. 2 is also going to be a miss because 2 currently is not present in the cache, so let's bring it in the second line and let's update these references. So 2 was also a miss. 3 is also not in the cache, so this is also going to be a miss. Let's bring it in line number 3, update the reference string. 4 is also not present here, so this is also going to be a miss. 4 is also a miss, and in response to this we bring in 4 here in the fourth line. Let's update the reference string. So mark a 1 in front of the fourth line and 0 in front of the other lines. Now 2 is also already present here, so this is going to be a hit. It hit in the second line, so update the reference strings. 1 is also already present in the cache, so this is again going to be a hit. It hit in the first line, so let's update this. 5 is not present in the cache, so this is going to be a miss. And in response to this we need to evict something, so let's find out the LRU line here. So line 1 was just now accessed, line 2 was accessed 1 cycle ago, 3 was accessed 1, 2, 3 cycles ago, and line 4 was accessed 2 cycles ago. So 3 is the LRU line, so let's replace this and bring in 5 over here. Update the reference strings. 6 is not present, so this is also going to be a miss. Let's evict the LRU line again. So in this case line number 4 is the LRU line because it was accessed 3 cycles ago, everything else was accessed more recently. So let's replace this 4 with 6 and update the reference strings. Next we access 2, so 2 is present here, so 2 will be a hit. It hits in the second line. Update the reference string. 1 again is a hit, so it will hit in the top line. Update the reference string. 2 is again a hit, so this is present here, so this will hit in the second line. Let's update the reference string. 3 is not present in the cache, so this is going to be a miss. In response to this miss, let's evict line number 4, because note that line number 4 was accessed 3 cycles ago. Oh no, actually line number 3, this was accessed 4 cycles ago, everything was accessed more recently. So let's evict 5 here and bring in 3 in place of 5. Again update the reference strings. 7 is going to be a miss because 7 is not present in the cache, so again let's evict the LRU line here. So these lines 1, 2 and 3 are recently accessed. Line 4 has not been accessed for 4 cycles, so let's evict 6, bring in 7 over here, update the reference string. So mark 1 in front of fourth line which was accessed and 0 in front of all the other lines. Now 6 was just now evicted, so this is again going to miss, and we now need to find the LRU line. So line number 1 is the LRU line which was accessed 3 cycles ago, everything else was accessed more recently. So let's evict 1 and bring in 6 over here and update the reference strings. Then we have 3 is present in third line, so this is going to be a hit, and let's update the reference strings. 2 is again a hit, it hits in the second line, so update the reference strings. 1, this is going to be a miss because 1 is not present anywhere, so let's find the LRU line for eviction. So this was accessed 2 cycles ago, this is recently, this is 1 cycle ago, this is 3 cycles ago. So let's evict 7. We'll evict 7 and bring in 1 over here. So update the reference strings again. Then 2 is a hit, it hits in the second line. Again let's update the reference strings. Then 3 is present in third line, so this will be a hit. is a hit, and let's update the reference strings here. Finally we have 6. 6 is not present in the cache, so this is going to be a miss. Okay, so let's count the total number of misses here. 1 2 3 4 5 6 7 8 9 10, and this is 11. Actually 6 is present in the cache, sorry about that. So 6 is present here, so this is not going to be a miss, this is going to be a hit. So 6 is a hit. So we actually have just 1 2 3 4 5 6 7 8 9 and 10 misses. So there were 10 misses with the LRU policy. This is also summarized over here, the same example. Next, let's work out the first in first out cache replacement policy. So once again we have this cache with 4 lines, which is fully associative, and this is first in first out cache replacement policy, and here is our reference string. So let's get started. Right now the cache initially is empty, so 1 is going to be a miss. So this misses, let's bring it in first line. And we are going to keep track of the order. So now, because this is not a least recently used policy, here we just need to keep track of the order in which these addresses were brought into the cache. So anytime an entry is brought into the cache, we'll mark a 1 in front of that line and a 0 in front of the other lines. 2 is, let's move on to 2. So 2 is also not present in the cache, so this is also going to be a miss. Let's bring it in the second line, and this was just now brought in, so let's mark a 1 in front of this line and 0 in front of all other cache lines. 3 is again a miss, 3 is not present in the cache, so let's bring it in the third line which is available, and let's mark a 1 in front of this line and 0 in front of all the other lines. 4 again is not present in the cache, so this is going to be a miss. Let's bring it in the last line which was empty and mark a 1 in front of the fourth line and 0 in front of all the other lines. Now 2 is accessed, so 2 is present in the cache, so this is going to be a hit. Now there is no need to update this reference strings here, because this is first in first out. It doesn't keep track of the recency of accesses, so so no change there. Now 1 is again present in the cache in the first line, so this is also a hit. 5 is not present in the cache, so this is going to be a miss. And now we need to figure out which line to evict. Now again, note that in first out, essentially the oldest line would be evicted. Now in this case, this line number 1, this is the oldest line. It was brought in 3 cycles ago. Everything else is brought in more recently. So let's evict line number 1 and bring in this 5 over here, and now mark a 1 here and a 0 in front of all the other lines. Next, 6 is not present in the cache, so this is again a miss. We have to evict something, so note that 1 was just now brought in. The oldest line that was brought in the cache was basically line number 2 in this case. So this was brought in 3 cycles ago. Everything else is more recent. So let's evict 2 and bring in 6 over here. Next we access 2, which is again going to be a miss. We just now evicted 2, so again we have to bring in 2 here. And actually I forgot to update the reference string after bringing in 6, so let's do that first. So let's update this reference strings, and now let's move on to 2. 2 is a miss, so now we have to figure out the oldest line, so which is basically line number 3. So let's evict 3. This was brought in 3 cycles ago, and bring in 2 over here, and let's update the references, the update strings, because 2 was just now brought in. Next we have 1 is not present in the cache, so this is again going to be a miss, and the oldest value is now 4. So let's evict 4 and bring in 1 over here and update this reference strings. 1 was just now brought in. So this is not a reference string, this is basically an entry string right now. It's just keeping track of when the values were brought in. It is not keeping track of the recency of access. Next we have 2. 2 is present in the cache, so this is going to be a hit. 3 is not present in the cache, so this is going to be a miss. The oldest line now is basically 5, so the line number 1. So let's evict 5 and bring in 3 over here and update the entries here. So this mark a 1 in front of line 1, and everything else mark a 0, because we just now brought in a value in line number 1. 7 is not present in the cache, so this is also a miss. And now we have to evict the oldest entry, which is line number 2 in this case. Let's evict 6 and bring in 7 over here and update the entry strings. So this mark 1 here and 0 everywhere else. Next is we reference 6. Now note that 6 was just now evicted, so it is not present in the cache, so this will also be a miss. 6 is going to be a miss. Now we have to evict the oldest entry, which happens to line number 3 in this case. So let's evict 2 and bring in 6 here, and update the reference string. Alright, after that we access 3 is present in the cache, line 1, so this will be a hit. 2 is not present in the cache, so 2 is going to be a miss. And now we evict the oldest line is now line number 4, which is entry 1 here. So let's evict 1 and bring in 2 here. So mark a 1 here. This is the entry update. Next we access 1. So 1 was just now evicted, so this is again going to be a miss. Now let's evict the oldest entry, which is now line number 1. So let's evict 3 and bring in 1 over here and update the entries. 2 is going to be a hit. It is present in the last line, so 2 was a hit. 3, this is again a miss. It's not present in the cache, so we have to evict something. The oldest entry now is line number 2, so let's evict 7 and bring in 3 over here. Let's update the entries. Finally 6 is present in line number 3, so this is going to be a hit. So using first in first out, we have a total of 4 plus 4 8 plus 3 11 plus 3 14 misses here. The answer is also summarized here. Finally, we have the optimal cache replacement policy. So let's begin working with this. Again, we have the same 4-line fully associative cache. So the first address reference to 1 would be a miss because the cache is initially empty, so this is going to be a miss. Let's bring in 1 in the first line. 2 is also a miss, so let's bring it in the second line. 3 is again a miss because it's not in the cache, so bring it in the third line. 4 again is a miss, bring it in the fourth line. Now 2 is present here in the second line, so this is going to be a hit. 1 is present in the first line, this is again a hit. 5 is not present in the cache, so this is a miss. Now the cache is full, so we need to evict something to bring in 5. Now recall, in the optimal cache replacement policy, we are here to figure out a replacement candidate. We have right now 1 2 3 and 4 in the cache. We will replace that line from the cache which is used farthest in the future. So note that address 1, this is again used, this is referenced 1 2 3 cycles later. Address 2, this would be referenced 1 2 cycles later. Address 3, this is going to be referenced 1 2 3 4 5 cycles later. Address 4 is going to be referenced 1 2 3 4 5 6 7 8 9 10 11 12 13. Never. So this is basically not in the near future. So number 4, this is going to be accessed farthest in the future, so let's evict 4 and bring in 5 over here. Next we have 6, which is also not present in the cache, so this is going to be a miss. Now again we have to do the same exercise. To bring in 6, we have to evict something. So we are here, now we look in the future for all of these 4 candidates, and the one that is accessed farthest in the future, that will be replaced. So 1 is going to be accessed 1 2 cycles later. 2 is going to be accessed just in the next cycle, 1 cycle later. 3 is going to be accessed 1 2 3 4 cycle later, and 5 is going to be accessed 1 2 3 4 5 6 7 8 9 10 11 12. Nowhere in the near future, right? So this is basically 12 plus. So again 5 is the one that we should evict and bring in 6 over here. Next we have 2, it is present in second line, so this is going to be a hit. 1 is again present in the first line, this is a hit. 2 is again present in the second line, it's a hit. 3 is present in the third line, it's a hit. 7 is not present in the cache, so it's again a miss. Now again we are here, we look in the future and figure out which of these 4 candidates present in the cache would be accessed farthest in the future. So 1 with respect to 7 is going to be accessed 1 2 3 4 cycles later. 2 would be accessed 1 2 3 cycles later. 3 would be accessed 1 2 cycles later. 6 would be accessed 1 cycle later. So in this case 1 is accessed in the farthest in the future 4 cycles later, so 1 should be evicted, and in this place we should bring in 7. Next we are referencing 6. It is present in the fourth line, so this is a hit. 3 is present in the third line, it's a hit. 2 is present in the second line, it's a hit. 1 is not present in the cache, it's going to be a miss. Now again, let's do the same exercise. So let's start looking in the future. We are here. 7 is not accessed. 1 2 3, it's 3 plus cycles. 2 is going to be accessed 1 cycle later. 3 is going to be accessed 1 2 cycles later, and 6 is going to be accessed 1 2 3 cycles later. So again, the first line is going to be accessed farthest in the future, so let's evict 7 and bring in 1 over here. So bring in 1 over here. Now next we access 2, which is present in the cache, so it's a hit. 3 is also present in the cache, it's a hit, and 6 is also present in the cache, so it's also a hit. So with optimal cache replacement policy, we had a total of 8 misses. The solution is also summarized over here. The last question here is about performance. We are given an unpipelined CPU which has a cycle length of 6 nanoseconds. This processor takes exactly 1 clock cycle to execute every instruction if the instruction hits in the cache. However, if the instruction misses the cache, then it takes 5 clock cycles to execute this instruction. For this problem, we are going to assume that every instruction accesses the cache. Now there are two parts to this problem. The first part here is asking us, if we have a 120 instruction program, how much time would it take for this processor to execute this program if the cache hit rate was 80%? And the second part is asking basically how much time would it take to execute the same 120 instruction program if the cache hit rate was 90%. And there is other part to the second part over here, and that is the speed up that this 90% hit rate of cache provides over the 80% hit rate in the cache. So let's start working on the first part. We know that the cycle length is 6 nanoseconds, and on a cache hit, the instruction takes 1 cycle to execute. However, if it is a miss, then the instruction takes 5 cycles to execute. These are the key points. Now the total number of instructions we have is 120. If the cache hit rate is 80%, this means 80% of 20, which is basically 96. So 80% of 20 is 96 instructions will hit in the cache, and the remaining 20%, which is basically 24, these will miss in the cache. Now let's figure out how much time these 96 instructions will take. We know that on a cache hit, the instruction takes just 1 clock cycle. So these 96 instructions will take a total of 96 into 1, these many cycles. Now each cycle is 6 nanoseconds. So let's multiply this by 6 to figure out the total time. So 96 into 1 into 6, this is actually 576 nanoseconds. Now what about the 24 instructions that miss the cache? So on a cache miss, we know that the instruction takes 5 cycles to execute. So these 24 instructions will take 5 cycles each. So the total number of cycles would be 24 into 5, and each cycle is again 6 nanoseconds. So multiply this by 6 to get the actual time. So 24 into 5 into 6 is basically 720 nanoseconds. So the total time it takes to execute this program on the processor with 80% cache hit rate would be 576 plus 720, which is basically 1296 nanoseconds. The solution to part 1 is also summarized over here. Let's come to the second part. The second part is asking what would be the speed up achieved if we can increase the cache hit rate to 90%. So let's first figure out the total time to execute the program if the cache hit rate was 90%. So once again, recall that the clock cycle length, the cycle length is basically 6 nanoseconds. If it is a hit, then it takes just 1 cycle. If it's a miss, then the instruction takes 5 cycles to execute. Alright, so our program had 120 instructions. If the hit rate was 90%, then 90% of 120 is basically 108. So 108 instructions would hit in the cache, these would hit, and the 10%, which is basically 12, these will miss in the cache. These 108 instructions will take just 1 cycle to execute. So the time taken by these 108 instructions would be 108 multiplied by 1, these many cycles, and each cycle is 6 nanoseconds. So multiply this by 6. So the time taken is basically 648 nanoseconds. On the other hand, these 12 instructions which miss in the cache, they will take 5 cycles each. So they will take a total of 12 into 5, which is 60 cycles, and each cycle is again 6 nanoseconds. So multiply this by 6 to get the total time. This comes to 360 nanoseconds. So the total time taken is basically, so total time is basically 648 plus 360, which is 1008 nanoseconds. So with 90% cache hit rate, the processor will take 1008 nanoseconds to execute this program. Now the question is, what is the speed up achieved over the 80% hit rate cache? So recall, speed up is again old execution time divided by the new execution time. So with 80% cache hit rate, the processor was taking 1296 nanoseconds to execute. With 90% hit rate, it is taking 1008 nanoseconds. So the speed up is 1296 divided by 1008, which basically comes to about 1.286. So this is our speed up. The solution is also summarized over here. This brings us to an end of the current deck of review questions. I may add one or two more questions to the review slides. Those would be updated on Canvas. However, this review slide deck is not a comprehensive list of all possible questions that you would get on the exam. So please, in addition to solving these questions, also go through all the lecture slides, all your class notes. Again, solve all the homework assignments, the midterm review questions, also the midterm exam questions. All of those solution for all of those questions have been posted on Canvas. If you have any questions, please let me know. Write to me. Thank you.